The fundamental rule for counting is that, let's see, E sub 1, it says, is an event with N sub 1 possible outcomes. E sub 2 is an event with N sub 2 possible outcomes. The number of ways the events can occur in sequence is N sub 1 times N sub 2. This principle can be applied for any number of events occurring in sequence. All right. That is the fundamental rule of counting. The example, your book gives a lot of examples, but one example your book gives, it says, a local office supply store offers ballpoint pens from 3 different manufacturers. Each manufacturer's pen come in either red, blue, black, or green, and either fine or medium tip is available for each color. How many different pens does the store carry? All right. So we have different colored pens, and then each pen can come in either fine or medium tip. So the way that we could figure out how many that the store carry says it also says that we have 3 different manufacturers. So 3 manufacturers, and then each pen comes in red, blue, black, or green, and then each tip is either fine or medium. So we have 3 manufacturers. Each of those have 4 pens, and each pen can have one of 2 tips on it. So that means 3 times 4 times 2, there are 24 different pens. Okay. All right, this is a pretty classic question. I've seen this question, this counting question, asked in a variety of ways, but it just makes you think a little bit. It says you have a stack of 5 textbooks. English, history, statistics, of course, geology, and psychology. How many ways can you arrange these textbooks on a shelf? All right, so we're going to arrange those textbooks on a shelf, and we have 5 different places that we're going to put those textbooks. Okay? When I choose one textbook, I have 5 to choose from. So there's 5 possible ways to choose the first textbook. Well, after I've already placed that textbook, then I only have 4 to choose from the second time. The next time I have 3, the next time I have 2, and then the last time I only have 1. So the possible number of ways to arrange 5 textbooks comes out to be 5 times 4 times 3 times 2 times 1, 20 times 6, that's 120. So there are 120 ways that you can arrange those 5 textbooks. Okay, that, not this problem, but this calculation that we just did 5 times 4 times 3 times 2 times 1, counting down like that and multiplying, has a special name. It's called factorial. All right, and so 5 with an exclamation point behind it, that means 5 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So any number factorial is going to be the product of all of the numbers less than or equal to that number down to 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? And so we have to use factorials to help us do other types of calculations, other types of counting calculations. The official definition in general terms, factorial, n factorial is equal to n times n minus 1 times n minus 2, and then you keep multiplying until you get to 1. So I'd say times 3 times 2 times 1. Also, by definition, to get all formulas to work out, 0 factorial is defined as 1. Even though 0 factorial, 0, there are no positive numbers less than 0. To get all formulas to work out, you get 1 for 0 factorial. So if you've ever used a calculator and seen that little exclamation point, that's what it means.
So it's the largest number or the first number, or I'm confused about how you choose what?
Oh, it really it depends on the problem, but let me get into how we use it, and maybe it'll make a little bit more sense. All right, so one type of problem or counting problem that we run into is the number of ways that you can order objects or choose objects. Okay? If we're worried about order, then that's called a permutation. Okay? So a permutation is a specific order or arrangement of objects in a set. All right. For example, I told you earlier, if we all went down to the football field and we all started racing and we wanted to know how many ways that we could come in first, second, and third place. Well, order would matter. Maybe you get first place or second place or third place. So it matters as far as what place you get. If I got first, you got second, and somebody else got third, that would be a different outcome from if somebody else got first, you got second, and I got third. Those are different outcomes. So, does order matter when races, when you're racing and things like that? Yes, order matters. The formula that we use for permutations, there's two ways I've seen this written. Actually, three ways. I've seen this written like this, where you have N, P, K. I've also seen an R here instead of a K. I've seen this written as N, P, R. They mean the same thing. K and R just stand for the same thing. N is the total number of items. K or R here, that's the number of items that are being chosen. So NPK is one way to write that. Your book writes it like this. It means the same thing. If you look at it in a calculator, in a Texas Instruments calculator, it's like this here, NPR. Again, means the same thing. So a permutation is equal to n factorial divided by n minus k factorial. Okay. So what type of counting problem will we use this with? I made a reference to a race. Here's a race problem here. Says 7 sprinters have advanced to the final heat at a track meet. How many ways can they finish first, second, and third? So, how many sprinters do we have? We have 7, right? So n is going to be equal to 7. Now that's just the number of sprinters. That's not n factorial, that's just n. Now, how many places are we looking at? First, second, and third place. Okay, so our k is going to be equal to 3. So this can be written, like I said, a couple of different ways. One way is 7p3. Your book writes this as a p with a 3 at the bottom and a 7 at the top. It's just a different way to write it. If we apply that to our permutation formula, that would be 7 factorial divided by 7 minus 3 factorial. So that's 7 factorial divided by 4 factorial. So in a race, order matters. So that's why we have to use a permutation. Now, if I want to calculate this, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. But let me show you something. Let me show you a way to help save you some time when you're calculating factorials or permutations. 7 factorial is 7 times 6 times 5 times 4, and then it's times 3 times 2 times 1. But you can stop at any number and put the factorial sign after it, and then do not write a number after it, right? So I can count this down to 4 factorial, and you say, why would you want to do that? Because my denominator has a 4 factorial. And so if I'm working these out by hand, and you ever have a fraction, if you count down the numerator to the factorial in the denominator, then those cancel out because of the way that multiplication and division work. So this calculation is 7 times 6 times 5. So if you were doing this out by hand, it's a lot easier to do 7 times 6 times 5. All right, so that's 210. So if I had 7 sprinters, there's 210 ways that those 7 sprinters could place first, second, and third in a race. All right. Whenever you have duplicated objects or items, so we wouldn't be talking about people because you can't duplicate people, right? But let's say that we had a big group of books and some of them were the same, but we were still wanting to know how many ways could we arrange those books. Then you have to use a different formula, and it is one for distinguishable permutations. And that formula is n factorial divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, so on and so forth to n sub k factorial. Okay, and so all of these in the denominator, the numerator of course is the total number of items factorial. The numbers in the denominator, let's say I had 3 history books that were the same, then this would be 3 factorial. Then I had 2 English books that were the same, then the next would be 2 factorial. And then all of my other books are different. Well, if they're all different, all these others are 1 factorial, so they don't make a difference. But if we have objects that are the same, and you want to know how many ways you can arrange those objects, you say the total number of objects factorial divided by, anytime you repeat something, you divide it by that number factorial. So let's say, how many ways could we arrange the word, say, Mississippi? So how many ways could we arrange the letters in the word Mississippi? All right, so first we need to know how many total letters are in Mississippi. So count all the letters. All right, I got 11. So our numerator is going to be 11 factorial divided by, all right, how many or which letters are repeated? We need to see, are any of the letters repeated? Of course they are. That's why we chose this word. There's only one M. So you don't have to put a 1 factorial in the denominator. That wouldn't do anything, but you can if you want to. How many I's are there? 4, right? So you divide by 4 factorial. How many S's are there? 4. Divide again by 4 factorial. How many P's are there? 2. Divide by 2 factorial. Now, you can't simply multiply factorials together. For example, 4 factorial times 4 factorial is not equal to 16 factorial. So you do have to expand these. One way, I mean, 11 factorial is a pretty big number if you think about it. But one way to give me just a few less calculations if I was doing this by hand is just to write this out to 4 factorial. Because one of the numbers in the denominator is a 4 factorial. And so I could cancel one of these 4 factorials out. So I still have to figure out what that numerator is equal to. It's 11 times 10 times 9 times 8 times 7 times 6 times 5. All right, so I get 1,663,200. And then the denominator is going to be 4 times 3 times 2 times 1 times 2 times 1. Right? 4 factorial times 2 factorial. So that is 24 times 2, 48. Right? So it's going to be that number divided by 48. And I should get a whole number when I do this because of the way that the permutations work out. I'm not going to get a fraction. I'm going to get a whole number, no decimal. So 34,650. There are 34,650 distinguishable ways that we can arrange the letters in Mississippi. Yes.
Why would you not put M?
Because there's only one M. So if there is only one M, you could put a 1 factorial down here, but dividing by 1 factorial is simply just dividing by 1. So we didn't use the M because it wasn't repeated. All right. Now, another type of counting is combinations. So we looked at a type of problem where order mattered. That was a permutation, like those racers, those sprinters. But what if order doesn't matter? So combinations is a type of problem or counting problem where order does not matter. We run into this a lot of times if we're choosing objects or choosing items. For example, if I wanted to choose a group of 3 people in this class, then if I choose, say, John, Sally, and Jeff in that order, or if I choose Sally, Jeff, and then John in that order, that's still the same group. So the order that which I choose them doesn't matter. That's a combination. So if you're choosing objects from a group and order doesn't matter, that's a combination. Like if I just wanted to randomly assign, let's say that we started our own club and we had president and vice president, then, and and I randomly assign that to two people, and they really didn't have any meaning, maybe they were going to be our leaders, but, you know, assigning president to one and vice president to the other, or vice president to one or president to the other, if I choose those two people, there's two different ways that I can choose those two people. You know, I can choose Jack and then Jill, or I can choose Jill and then Jack. I have the same two people. So when you're choosing objects like that, and order doesn't matter, it's called a combination. And I don't know why I misspelled that. I put an extra letter in there. All right. Now the formula for combinations, again, the way that I usually see this written is NCR, and that's the way that the Texas Instrument calculators have it. But you can have NCK. It means the same thing. Or your book, it writes your C, your K at the bottom, and your N at the top. But that formula is very similar to the permutations formula. It's just a little different. It's n factorial divided by n minus k factorial times k factorial. So you can see we're dividing by an extra factorial in the denominator. So combinations will always be less than permutations. I would say less than or equal to permutations. All right, here's an example about the lottery. Of course, to win something like the Powerball, you have a better chance of being hit by a meteor or struck by lightning twice. But some of the smaller lotteries you actually, could win if you were lucky enough. I read an article that showed, I think it was 2 different people that had won 2 lotteries of a couple million or more. So those people were really, really lucky. Or who knows, maybe they shouldn't have won. Maybe it made them into a different person. Anyway, this problem says, in South Carolina's Carolina 5 lottery, a player selects 5 different numbers, so 5 different numbers from 1 to 36. Inclusive, meaning you can choose 1, you can choose 36. If the numbers selected match the player's numbers in any order, the player wins. So with the lottery, you don't have to have the numbers in order. It would be, nobody would ever win. There'd be very few lottery winners if order mattered. Okay? If you've ever seen a Powerball ticket or bought a Powerball ticket or something, it's almost impossible to win that, but it's even more impossible to get them in the same order that they're chosen. Okay, so this is a combination. We have 36 different numbers to choose from. How many are we choosing? 5, right? So the combination is, it's 36 C5, like that. Or the way your book would write that is C sub 5, got a superscript or an exponent here that kind of looks like 36. It's not really an exponent, but it's written in that place. Alright, so that would be 36 factorial divided by 36 minus 5 factorial times how many are we choosing? 5. So it's times 5 factorial. Now, in most calculators, if you just try to find 36 factorial, it's going to probably give you a scientific notation answer because that number is so big. So let's see. I don't know if my little simple calculator here has a factorial button. I don't. Am I right? Yeah, there it is. So you can see even this calculator that has about 3 times as many places or 2 times as many places as normal calculators writes this as 3.71, basically 3.72 times 10 to the 41st power. Alright, well, probably don't want to write in that answer as your numerator. But what we can do, let's simplify the numerator. So that's going to be 36 factorial over 31 factorial times 5 factorial. Now, let's simplify the way that I showed you earlier. So count down the numerator. This is 36 times 35 times 34 times 33 times 32 times, I'm not going to go all the way because what? I'm going to stop at 31 factorial because that is one of the numbers in the denominator. And so my 31 factorials will cancel out like that. So now I'm just left with this, which is still a big number, divided by 5 factorial. Okay, so 36 times 35 times 34 times 33 times 32 equals, that's still a pretty big number, 45,239,040 divided by 5 factorial. 5 factorial is what? That's going to be 120. So this is going to end up being 45,239,040 divided by 120. And we better get a whole number. Alright, so I got 376,992. 376,992. So what that means is, if I was to purchase one of these lottery tickets and go in there and write down my 5 different numbers that were between 1 and 36 inclusive, then there are 376,992 ways that I could select those numbers. Now, part B is interesting. It says, what is the probability of winning? Alright, so the probability of winning, there's only one correct set of numbers out of that many types of numbers. So it's going to be 1 divided by 376,992. So you can see it has to write this as scientific notation because it's so small. It was times 10 to the negative 6. So I'd put 5 zeros, 0.00000, and then 265, I'll leave it there, 265. Really small probability. You know, if you think about that as a percentage, that's still 0.000265%. It'd probably be about the same probability as me walking across campus and finding $1 on the ground. You know, just that doesn't happen, right? Nobody's going to leave money on the ground. Yeah, in the book they rounded to 3, but it's rounded. I put my little squiggly marks here, so I'm good. All right, there is a little table that is in your book, but everything in the table is basically on your formula sheet. It just kind of summarizes these different rules. Telling if a problem is a permutation or a combination is going to depend on whether order matters or order doesn't matter. Okay? If order matters, then it's a permutation. If order does not matter, it's a combination. So, I guess an easy way you could remember that would be if you can just kind of associate combination with lottery ticket, then the order that you choose the numbers on your lottery ticket doesn't matter. That's a combination.
And since we have 11 people today, if I want to know how many two-person groups I could form, unique two-person groups I could form out of 11 people. Order doesn't matter. If order matters, then it matters, you know, if I select one person, then another person, or if I do it the opposite way, that would be two groups. Well, if order doesn't matter, it's a combination. So it's 11C2. Most calculators have that shortcut, but if you didn't use the shortcut, and we use the formula, that would be 11 factorial divided by 11 minus 2 factorial times 2 factorial. So this is my n, and this is my k, or my r, depending on what you want to call it. All right, so one way that I could do this out longhand, I could do it out longhand pretty fast, is that I'll have 9 factorial times 2 factorial. So you step the numerator down until you get to 9 factorial. So 11 times 10 times 9 factorial. And then these cancel out. And so all I have is 11 times 10 divided by 2 factorial. 2 factorial is 2 times 1. So that is 110 divided by 2, or 55. So there's 55 unique groups of of two-person groups that I could make in this class. In the formula we say this is n minus r, n minus k. So how did I get, so remember factorial, what it means is you're stepping down and multiplying like this. And so I could stop at any point. Like I don't have to put times 8 times 7 times 6. I could stop at 9 and just put 9 factorial, because 9 factorial stands for 9 times 8 times 7 times 6. And the reason that I stopped there was because I had a 9 factorial in the denominator and it would cancel out. So if you're not using technology to do it, it's always good to cancel out. Otherwise, if I didn't use any shortcuts, I would do this right here, and this takes a lot longer, and sometimes if the number gets too big, the calculator will start putting things in scientific notation, and so I don't want to have to do all of this. And then I'd say times 2 times 1, you know. I don't want to do all that in the calculator, even though I could, and I'll get the same answer. I just used a shortcut and stepped it down. All right. So I'm going to look at a little bit of the homework. Here's just flat out, this isn't a word problem. It just says evaluate the expression. And it gives this permutation here. You just got to either use your technology to do it or work it out with the formula. And the formula, remember, it's n factorial divided by n minus k or n minus r, whatever you want to call it, factorial. There's n and there's r, or there's n and there's k. So if I wanted to do that, it's 13 factorial divided by 13 minus 4 factorial. Now notice it's not the same as the combination. I don't put the 4 out here again. Okay, so you can do this in the calculator a lot faster than I can do it writing it out. So what is 13 minus 4 is 9. So again, I'm going to stop my numerator at 9 factorial so that I can cancel the 9 factorial out in the denominator. So then I just need a calculator to do this. So that's 13 times 12 times 11 times 10. So I should get 17,160. And so if you want to try to put some context into that and make a problem that kind of sort of makes sense in your mind, okay, so if order doesn't matter, if there were 13 students in this class and I wanted to choose groups of 4, there would be 17,160 ways for me to choose those groups of 4. That doesn't take into account that some of the groups would be the same because they would just be the same people chosen in a different order, but that's what the problem said. It was a permutation, not a combination. So let's work through another combination. I would be practicing with my technology if I were you. If you don't have technology, then you can always come grab a calculator, because we're going to do a lot more permutation and combinations where you know how to do it in a calculator. It's going to make it a lot easier than having to work it out by hand every time. All right, so this is a combination. So with combinations, order matters. So order does not matter, sorry. So since order does not matter, then this number is going to be a little bit, or probably a lot smaller than if it was a permutation. So its formula is n factorial divided by n minus k factorial times k factorial. Where here's our n and here's our k. So this is 12 factorial divided by 12 minus 6 factorial times 6 factorial. So that's 12 factorial divided by 6 factorial times 6 factorial. Now you can't multiply the 6 times the 6 and get 36 factorial. It doesn't work like that. Okay? Working this one out by hand is actually going to take me a little bit longer than the previous problem. Because what I'm going to do is I'm going to count down all the way to 6 factorial. So I have to write all these numbers that come before 6. I'm going to stop at 6 factorial. And then the denominator I have 6 factorial times 6 factorial. So I can cancel one of those out. So now I need to multiply all these numbers and divide by 6 factorial. And you can write out 6 factorial if you want to. You don't have to. So 12 times 11 times 10 times 9 times 8 times 7. See how big the numbers are getting? Then I'm going to divide by 6 factorial. So I do have a factorial button on here. So I'm going to say divided by 6 factorial equals 924. So what that means, you know, if you try to put a little try to make a problem up so that this would make sense in the real world. If there were 12 students in here, and I wanted to divide, or I wanted to get a 6-member group, then, and order doesn't matter, there would be 924 ways to form a 6-member group. All right, let's see. Let's look at this word problem and see if we can figure out what it's asking. All right, so this says, how many ways can Carlos choose 3 pizza toppings from a menu of 4 toppings if each topping can only be chosen once? So how many ways can he choose? Well, this is going to be a permutation, okay? Because the ways you can choose something, you can use different orders, right? So this would be 4p3, or 4 factorial divided by 3 factorial. What? No. That's not right. That's not right. This is not a permutation. I'm just thinking. Okay, so we're going to choose 3 toppings. Out of a menu of 4 toppings. And each one can only be chosen once. So I don't even think this is a permutation or a combination. So how many ways can he choose this? This might be this isn't a permutation. I don't think this is a permutation. This is a combination. This has to be a combination. So this here. How many ways can he choose? So does the order matter? The way that he chooses those, does the order matter? And the answer there is no, because think about it. Okay, so let me just like make up some toppings. How about we do that? This is awesome. I got my pizza here. So I'm going to have pepperoni. I'm just going to say pepperoni, sausage, bacon. Everybody loves bacon, right? What's a good vegetable to put on a pizza? Spinach.
Could you do this as a counting problem?
How do you spell spinach? There we go, spin. Could we do it as a counting problem? Each one could be chosen once, but how would we be able to take out those? All right, so here's why I wrote these down. So if I choose pepperoni, bacon, and spinach, or if I choose bacon, pepperoni, and spinach, those are the same pizza, right? So each topping can only be chosen once. That is right. So it couldn't be bacon, bacon, bacon. Or that'd be the best pizza. So this is a combination because we would want to get rid of those duplicate groups that are the same toppings. Okay. So if we treat it as a combination, then we can figure out just how many different pizzas we could have. So that would be 4 factorial divided by 4 minus 3 factorial times 3 factorial. So that's 4 factorial over 1 factorial times 3 factorial. Or 4 factorial, or let's say 4 times 3 factorial over 3 factorial. And that's the answer that I have in the book, or that I have from the homework, so 4. And I guess that leaves a little room for interpretation. Maybe it should have said instead of saying if each topping can only be chosen once. I mean, I see why they say that, but maybe distinguish that, or say that, if the toppings are the same, then it doesn't matter the order that they're chosen, or something like that, to lead you on to understand why you actually get that answer. So let's look at the next problem. Seven cards are drawn from a standard deck of 52 playing cards. How many different 7-card hands are possible if the drawing is done without replacement? So if the drawing is done without replacement, what does that mean? That you can't have a duplicate card, right? So there are 7 cards drawn from a standard deck. How many different 7-card hands, I guess, are possible if done? So you draw a card, or you draw 7 cards, and you look at your hand. You can put those back, but it's saying it. I believe what it's saying is, when you draw a card, you don't put it back before you draw another card, which you wouldn't anyway. So I don't really know why it tells us that without replacement. I guess this would be a counting problem, would be the easiest way to do it. Kind of use common sense. How many different cards are there? There's 52, then there's 51, then there's 50, then there'd be 49, there'd be 48, 47, and then 46. So you could think about this just like a counting problem. Another way to think about this would be a combination? Let me see what this answer is. Anybody multiplied that yet? Did you get 133,784,560? Yeah. All right, so that's the answer. Now, what do you get if you try 52 factorial divided by 52 minus 7 factorial times 7 factorial? Just do the combination 52C7 and see what it gives you. So you can think about it either way. You can think about it like kind of in a common sense, intuitive way, and just put the blanks up there and figure it out. Or you can make it the problem 52C7. Right? Because if you have a hand, it doesn't matter the order that you drew the cards. If you have that hand, it's the same regardless of the order that you draw the cards. If that makes sense. Like if I draw 4 2s and in a row, and then I draw 2 kings, well, that'd be the same hand if I draw a king, a 4, a king, a 4, so like if I drew it in a different order, it'd still be the same hand. So that's why it's a combination. Oh man, this one might take a little thinking. Let's see. First time I read it, my head kind of, my thoughts went cloudy. All right, this says you're getting ready to line, okay. You're getting a lineup ready for a school kickball game. You have 5 girls and 5 boys. The rules state each child must kick the same number of times and alternate girl-boy or boy-girl. How many ways can a lineup be made for one round of kicking? So is there any way that we can... I don't think that the, like, I don't think that the order will matter, but we do have to have, like the people's names won't matter. I guess that would make different groups though. So, just wondering how will it, so I could figure out how many ways to line them up if I didn't have to do it boy, girl, or girl, boy. I could figure that out. And that would be so let's think about it. So it doesn't matter if you start boy, girl, or girl, boy. So you have 5 choices for the first, and then you're going to have 5 choices for the second, right? Regardless if you start with a boy or if you start with a girl. Because you're going to have to do a boy, girl, or a girl, boy. Then you'll have 4, then you'll have 3, then you'll have 2, then you'll have 1. That's just the way my mind analyzes this problem. So it really doesn't, you know what, I bet I can figure out how to write that as a permutation. Not a permutation, yet it is a type of permutation, I think. The answer, let's see what the answer is, and then we'll see what that is. The answer is supposed to be 28,800. So did anybody multiply that? 5 times 5
5 times 5, 4 times 4.
times 4 times
14,000.
Okay, so this would be the way, like if we went boy, girl, boy, girl, boy, girl, boy, girl, boy, girl. Okay. So then you have girl, boy, girl, boy, girl, boy, girl, boy, girl, boy. So that's two different ways to line it up because it says you can alternate either way. So that's why it's 14,400 and then times 2 would be 28,800. Now, that's a little confusing, right? Let me try one other thing up here to see if I can tie this into a permutation.
So these are questions from like our homework,
Mm-hmm.
so they're gonna do this hard.
Yeah, that's why I'm going over them. So they should be these types, though.
So you said this was with a permutation, right?
I was thinking, how could we make it into a permutation?
Because when I type Bob, NPR, Bob, in my calculator, it comes out 120.
It comes out what?
120.
5.
NPR, Bob. It comes out 120.
Yeah, that does, because that's 5 factorial divided by 5 minus 5 factorial. So when you type in that, when you're typing in this is what you're doing. And so that's 5 factorial divided by 0 factorial, which is 120. Is this is 1.
Well, shouldn't it come out 28,800 if that's the answer?
Yeah, but this isn't just a simple, like, okay, for this problem to be this kind of permutation, there's different types of permutations, then it would have to be like, we're just choosing 5 people, and then there's 5 ways to choose the first, 4 ways to choose the second, 3 ways to choose the third, 2 ways to choose that one, and then 1 way to choose that one. So then the answer would be 120. But the problem is that we have to line 10 people up in a line to kick a kickball. We have 5 girls, 5 boys, and we need to alternate. It needs to be boy, girl, you know, and so on and so forth, or girl, boy, and so on and so forth. So that's what makes this word problem kind of unique. It's the reason why it's a little unique here is because there's 2 different ways to line them up. So I was trying to figure out, instead of just using my math sense and putting blanks up here, I mean, I haven't seen this work anywhere, I just made it up. Instead of doing that, is there a way we could change it into a permutation or a combination where it would make sense? So that's what I was trying to figure out. I was thinking we had 10 factorial items, and then we had 5 of one and 5 of the other, but that doesn't take into account that you have to alternate. This is really what makes the problem a lot different from anything that we've done, is that you have to alternate between girl and boy or boy and girl. If you didn't have to alternate, then we could figure it out. So I believe, let me think for a second or two longer. Okay. And this is the easy section on counting. Remember I told you there was a 12A and a 12B? This is 12A. The other section is a lot harder. Yeah, I do not see an easier way to work this problem than, and I'm sure there is something you can come up with, but I do not see an easier way to do it other than writing it down, understanding what we're putting in these blanks. This could be one of 5 boys, this could be one of 5 girls, and then it's counted down, so on and so forth. Or this could be one of 5 girls, and this could be one of 5 boys. So this is the only way I see to work this problem. But I'm sure there's some kind of tricky way you could set up some kind of sum or some kind of difference in permutations and figure it out, or combinations. I just don't see it. The only way I see it is by working it out by just using counting principles and math sense. All right. That's problem number 9, by the way, in case you get that one. A lot of these problems are, like I worked just a permutation earlier. Like there's one like this, there's a combination, there's one like this, there's a permutation. And then we just did this one. But I mean, look at the next one. It's just work this out. 10 factorial divided by 3 factorial. So remember, you can do that in your calculator. That's when you would want to use the exclamation point in your calculator. So that would be the quickest way to do that. All right, so 604,800. The next one is the same thing. It's just a calculation. It didn't call it a permutation or combination. See if you can do this one. I'll give you about a minute or so to see if you can figure out how to punch this in. All right, what'd you get? 10? 210? Okay. So if you didn't get that, you need to figure out what's going on in your calculator. All right, now look at this. We're going to have to do this sum. We start dealing with probabilities that require us to do combinations and permutations. So definitely 10 times easier to do this in your calculator than to do it out by hand. But I'm going to write the formula you would use if you were doing it out by hand. And we will get a decimal here because you're dividing combinations. I say you will, but I would just assume, unless they chose regular numbers, or special numbers, that would let's see if I can do it in the calculator without working all that out. Let's be divided by All right, so if I round this to, it would depend on what the directions say. They'd probably say round to like 4 places or 5 places. If I round to 4 places, it'd be 0.0014. It's about. Like the boy, girl, girl, boy. Let me see if I can find another one like that. Why don't I have a 6 factorial on the bottom? Because this is a permutation. I see a couple of problems, like division problems like this. 1, 2, 2 of those on here. Let's see. I'm regenerating a new problem for, yeah. So here's a new girl, boy, boy, girl problem. So now we have 14 people in a line. Yeah, did you figure out a way to put it in?
I figured out how to do it.
2 times 7 factorial. Line up either girl, boy, or boy, girl. You got 2 ways to line them up.
Mm-hmm.
There's 7 different ways in each one. So 7 factorial times 7 factorial.
Awesome. So there's the shortcut for that type of problem. Ever how many boys and ever how many girls you have. 7 I guess, I wrote down that. We just didn't come up with that formula. That's very good. 7 factorial times 7 factorial times 2. Because you either start boy, girl, or girl, boy. What I was about to do is put numbers up here. I was going to put 7 times 7, 6 times 6, 5 times 5, 4 times 4, 3 times 3, 2 times 2, 1 times 4. But yeah, in the calculator, you put that right there, it'll spit out the answer. 50 million. That's about what I make a year. 803,200. All right. The only other type of word problem I see is this one right here. All right, and you can work this one out by doing 11C10. All right, so let's get 11. All right. The rest of them, like I said, are very similar to those. So I might have lied. Here's one more other type of problem. It's just a counting problem though, so I don't think y'all have problems with that. It's like, it says there are 4 types of drinks, 4 types of sandwiches, and 3 types of chips. How many different value meal packages are possible? So it's 4 times 4 times 3. 48. So if you have, if you had 4 bags of chips at home and you had 4 sandwiches at home and you had 4 different types of drinks at home, you can make 48 different meals with that. You say 4 times 4 times 3. That's the very first problem, though. Anyway, that's 12, section 12, so 6.12a. And now we're going to start chapter 7. Don't have a lot of time. We'll just go through a little bit. Now, I want you to just, before we start on this, look at the very last page, okay? So some of this stuff that we were just doing, don't look, let's see, look on the front of the last page. There should be a number 2 in the bottom right-hand corner. And I'm not trying to scare you, I'm just showing you that some of these calculations that we've been doing, we're going to use in certain types of distributions. So here's one of the problems here. And they're using this vertical notation, which I don't like. So this would be this times this over this. Always remember the bigger number is going to be on the left. That's how you can kind of, if you want to write it like your calculator sees it. And so, can I do that out by hand? Yeah, I can do that out by hand. But do I want to do that out by hand? No, I don't want to do that out by hand. So that's why it's important that you learn how to use your calculator, because then, at worst case scenario, you write down the answer for the first combination, the second combination, and the one in the denominator, and then you multiply out the 2 and you divide. But the TI calculators will handle all of those at once. You just put each combination in parentheses and put in the appropriate sign, division sign and everything. So we're going to have to do stuff like that at the end of this chapter. That's why we were learning it or going over it now, is we use that in a hypergeometric distribution. All right. So I am going to start chapter 7. I'm not going to try to push you too hard because our brains have been stretched a little bit today already. I think some of us are already on spring break mode. I know I am. Well, you can see that we don't have but about half the people here today, so but you're the lucky ones. You're all the important people. You're all here today. Just kidding. Everybody's important. All right, so this chapter is on probability distributions. Probability distributions. I'm going to just read through the chapter problem really quick, because the book will make reference back to this chapter problem lots. So it says, the notations of randomness and uncertainty were introduced in chapter 6. This chapter extends those ideas by developing concepts to describe a pattern of randomness for an entire set of outcomes produced by some random phenomenon. In the coin tossing experiment, the description was rather easy. The totality of outcomes contained only 2 values, heads or tails. Probabilities for these events were constructed by assuming a fair coin and by applying the classical definition of probability. So this will be the probability distribution for tossing a coin. You have your 2 variables right here, or your 2 outcomes, heads and tails, and then the probability of each one of those. Notice that when you sum up the probabilities, you do get 1. To analyze more complex random phenomena requires a method of organizing information about random processes and a vocabulary to describe organizational concepts. Two such descriptions will be introduced in this chapter: random variables and probability distributions. All right, random variables considered in this chapter will always be quantitative. So, quantities, quantitative. Outcomes will have numerical answers. Specifically, a probability distribution connects a probability to each value in the random variable, or each value the random variable can assume. All right, so we are on our way to different types of probability distributions. And a random variable is just what it sounds like. A numerical outcome of a random process. Okay, so any type of process that is random, I mean, I know there's science behind it, but like births, you know, you don't know if it's going to be a boy or a girl, and there's a reason why it is a boy or a girl, but it's pretty random, right? You know, if you have, you know, 4 children, you can figure out the probability that you would have 0 girls. You can figure out the probability that you would have 1 girl. You can figure out a probability that you'll have 4 girls. I have a friend that has 5 girls. 5 births, 5 girls. So overall, statistically, that's a very small chance that that's going to happen. But there are ways to figure all of that out. A probability distribution is a model which describes a specific kind of random process. A discrete random variable is a random variable which has a countable number of possible outcomes. These are just terms that we'll be using. And then the example they give: random phenomenon. Toss a die and observe the outcome for the toss. So the outcomes, the sample space, 1, 2, 3, 4, 5, 6, that would be the different values of x, right? So if we were trying to describe this process, here are the possible outcomes. And then I could also extend this table to include the probability of getting x. So 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. Right, so here is an example of a simple probability distribution. We know that the sum of all the probabilities has to add up to be 1. Okay? And in this case, all of the probabilities are equally likely. The random variable there is the numbers 1, 2, 3, 4, 5, and 6. And then the outcomes, their probabilities, are listed there as well. Real easy concept to understand. All right, so the next example says random phenomenon. The number of defective integrated circuits received in a batch of 1,000. Each outcome of the random variable is a numerical measure whose range of values is given below. First, it says let x be the random variable equal to the number of defective integrated circuits in a batch of 1,000. So, anybody ever seen an integrated circuit? Like a little IC chip? If you've ever seen a motherboard, if you've ever taken anything apart and you see these little, usually the tops of them are kind of black and they're like soldered into the board. Those are little integrated circuits. Okay? You could do all kinds of cool things with different integrated circuits. All right. the range of values, integers between 0 and 1,000. So that would be the number of defective chips. You're going to have, if we wanted to make a table, we would have a table with X and list our random variables, be from 0 to 1,000. Okay? And then the probability, we don't know. We don't know what the probability is until we actually own a business and we see over a large amount of time how many chips are defective. And then we can figure out the probability of having exactly 5. Or usually you wouldn't want to know something like that, exactly 5 defective chips. You'd want to know something like, okay, if I produce 1,000 of these integrated chip circuits or whatever, these little integrated integrated circuits, then what's the probability that less than 5 would be defective? That would probably be what I would want to know. And so if I want to know the probability of less than 5 being defective, I would have to say the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. Okay? So we want to know things like that, especially if you have a business. You want to know how many defective items that you have, because you have to replace those defective items. All right. Here's another example. Random phenomenon. The head nurse of a pediatric division of the Sisters of Mercy Hospital is trying to determine the capacity requirements for the nursery. She realizes that the number of babies born at the hospital each day is a random variable. She will have to develop a description of the randomness in order to develop her plan. So it says X equals the number of babies born at Sisters of Mercy Hospital each day. And so then your range of values that you would have for your random variables would be between 0 and then whatever the largest number is. Maybe she goes back in the records and she checks the number of babies born each day for the past year. And so she finds the largest number of babies that have ever been born, and can figure out probabilities of a day where 6 babies are born, or a day where 10 babies are born, or a day when less than 6 babies are born. And you can figure out the probabilities of all these things happening. So this is kind of just setting up the rest of the chapter and how to figure out that kind of stuff. A continuous random variable is a random variable that can assume any value on a continuous segment of the real number line. If it's continuous, there is no value that could be assigned to that variable. The next example, it says Cisco's, a local Mexican restaurant, has an express policy that states that lunch will be served within 15 minutes of ordering, or it will be free. Obviously, the restaurant is keenly interested in not giving away its product and in delivering on its promise of a timely lunch. But the length of time to prepare each meal varies because of the difference in preparation times of each dish, the load on the kitchen, and the experience of the chefs and waitresses. Since time is measured on a continuous scale and the variability of meal preparation is not predictable, the time between ordering and receiving a meal is considered to be a continuous random variable. And so then you'd have that random variable, it'd be the time between ordering a meal and receiving it. And then, it says between 0 and infinity, and 0 probably would not be very feasible. I guess if somebody came in and all they wanted to do was order a basket of chips and a glass of water, that would not take any time, right? If somebody just greeted you at the table and that was it. But that's not going to happen very often. All right, and that finishes up section 1, and that is where we will stop.